Okay, so we're going to continue our study on polynomial functions and their graphs, and this is going to be part 2 of our lessons dealing with polynomial functions. Now, in this objective, basically we're interested in determining the end behavior of the graph of a polynomial function, and we're going to do this by using the leading coefficient test. Now, as we go through this, we're going to look at examples of polynomial functions and their graphs, and we're going to discuss this end behavior using those graphs. Now, before we go on, let's kind of review real quick from part 1 what a polynomial function is. So recall that a polynomial function, and remember, a polynomial function has degree, and the degree is the largest exponent of the variable that you would see. And so a polynomial function of degree n is given by this expression. So it looks gibberish, but basically it has all these terms. And one of the things we saw that the exponent of these variables must be whole numbers. Okay, so they cannot be negative, they can't be fractions or anything like that. They must be strictly whole numbers. And this term here, this term that has the largest exponent, that's called the leading term. All right, so that's going to be important in our discussion as we go through this. So that's called the leading term. And recall a sub n is called the leading coefficient. Okay, so notice though that in the examples we're going to look at, some of them will be in standard form, where it's listed term by term. And notice that the polynomial functions that are in standard form are in descending order. And so if you look at this term here, the 4x squared, that's the leading term of this polynomial. And over here, negative 6x to the 5th would be the leading term of this polynomial. Not because it's listed first, but because it has the largest exponent. So the degree of this function is 2, because it's the largest exponent that you see, and the degree of this function g of x is 5, because that's the largest exponent you see. So we can write polynomial functions in standard form or factored form. Now, f of x and g of x are in standard form, but k of x and h of x are in factored form. So you see, you'll notice that they're listed as a product of factors. Okay, so what we want to do though is kind of remind ourselves, well, how can I find the leading term of a polynomial function that's factored? How can I find the leading term of h of x? I know how to find it if it's in standard form. That's easy. F of x and g of x, that's easy. But what about k of x and h of x? So that's something that we're going to have to discuss as we go through this. But remember, the whole goal of this is to use the leading term to determine the end behavior. Okay, so that's going to be our goal for this lesson. So recall from part 1 that polynomial functions have graphs that are smooth and continuous. So recall that there are no breaks, there are no gaps in the graph, and there are no sharp turns. Like the absolute value function is not polynomial because it has a sharp turn. So these are things that we discussed in part 1. But pay close attention to the fact that polynomial functions have graphs that are smooth and continuous. So as a review from part 1, here's some examples. So let's suppose we had this polynomial function. So it looks something like this. Let's say it looks like this. All right, so that's an example of a polynomial function. So notice that it's smooth and continuous. All right, here's another example. So we could have something that looks like this. Just like that. All right, so notice it's smooth and continuous. Notice that the turns are smooth. The turns are smooth. And again, we could have something that looks like this. We could have something that looks like this, let's say. So notice the turns are smooth, and the graph is continuous. And I want you to realize that when you are dealing with polynomial functions, the domain is all real numbers. So you see those two arrows on either end? So that's because the domain is all real numbers. So the domain of a polynomial function is all real numbers. All right, so the domain of a polynomial function is all real numbers. Okay, so remember in an interval we're listed as negative infinity to infinity, and notice the parentheses when we talk about infinity, negative infinity. Okay, so just remember that the graph of a polynomial function is smooth and continuous. There are no breaks. Okay, so when we talk about the end behavior though, now here's what we mean by end behavior. So the end behavior, or at the ends of the graph, what's happening? See, this is what I mean by end behavior. It doesn't matter what happens in between. I don't care about that. When we talk about end behavior, I'm interested in what's happening on the ends of the graphs. Okay, so that's what I mean by end behavior. Okay, so the end behavior of a graph was defined to be the behavior of the graph of a function to the far left or the far right. So basically you're looking at the left and the right of the graph of the function. So for example, let's look at this example. And now as we go through this example, make sure you are listening to the terminology that we're going to be used, or you make sure you understand the terminology that's being used. So if I look at this polynomial function, and so I know this is a polynomial function because it's smooth and continuous, I want to look at the end behavior. Now remember, the end behavior is this. So the behavior of the graph at the far left and the far right. Okay, so that's what I mean by end behavior. What's happening between that is not our interest right now. All we're interested in is what's happening on the outsides of this graph. And basically, you're just looking at the part of the graph with the arrows. That's all you're looking at. Okay, so listen carefully to this. So here is the way that we're going to describe the end behavior. All right, now listen carefully. So remember, your domain is all real numbers. Okay, so remember the domain's all real numbers. So as x goes, this arrow here means goes, as x goes or approaches positive infinity, so meaning this, so as x gets bigger and bigger and bigger and bigger, that's what that means, okay? So as x approaches infinity, so as x approaches positive infinity, what are those y values doing? That's the question. So look at your y values. My y values are getting more positive, right? See, they're getting more positive. These are your negative y values. These are your positive y values. So they're getting more positive. And I'm going to go ahead and call this function f of x. So let's just call these functions that we're going to look at f of x. So as x approaches infinity, comma, f of x approaches infinity. Okay? So f of x approaches infinity. So meaning that f of x, the y values are getting more positive. So as x gets more positive, my y values get more positive. Okay? Now let's look at the other side. So this is the right behavior. Now let's look at the left behavior. Okay, so as x approaches, now remember this time we're going this way. So we're looking at this side. You understand? Looking at this side. So as x approaches negative infinity, so here's your x-axis, here's your y-axis, so we're getting more negative. So as x gets more negative, okay, meaning this, comma, f of x, my y values are doing what? Well, my y values are getting more positive also. All right, so you see there your arrow is pointing up. So if your arrow is pointing up, that's going to mean your y values are getting more positive. They're getting bigger. Your y values are getting bigger. They're getting more positive. Okay? All right. Now, here's something is going to help you with this. Notice that in this polynomial function, your arrows are pointing up. Your arrows are pointing up. Okay? So that means that as x gets bigger, your y values get more positive. As x approaches negative infinity, your y values are positive. So if your arrows are pointing up, your y values are getting more positive. Okay? All right, now look at this one. Now notice this time you have this polynomial function. You know it's a polynomial function because it's smooth and continuous. And again, let's just call this f of x. So let's look at the end behavior. Now remember what we mean by end behavior. When we say end behavior, I'm interested in what's happening on the far left and the far right. Okay? So we're going to use that same notation. We're going to use that same notation as x approaches infinity. Now remember what we mean by that, as x approaches infinity. So as x approaches infinity, meaning that as x gets bigger and bigger and bigger and bigger, what are those y values doing? As x approaches negative infinity, what are those y values doing? Now remember, y means the same thing as f of x. Okay, you got to remember that. So remember in the first example, the arrows were both pointing up. Okay? In this example, our arrows are pointing down in both situations. So as x approaches infinity, as x gets bigger and bigger and bigger, what are those y values doing? What is y value approaching? So my y values are getting what? They're getting more negative, right? So they're getting more negative, so meaning negative infinity. So your y values are approaching negative infinity. Okay, now let's look at this side. So as x approaches negative infinity, so as x gets more smaller, as x gets smaller and smaller and smaller, what are those y values doing? Well, those y values are going, this arrow is going down, right? So your y values are getting more negative. All right, so that means f of x is approaching negative infinity. So the pattern for this is this. So if your arrows are pointing up, notice what your y values are doing. Your y values, so the arrows are pointing up, the y values are approaching infinity in both cases. If your arrows are pointing down, your y values are getting more negative. Okay, so they're getting more negative. So hence negative infinity. All right, now let's look at this example. So in the first example, our end behavior, the arrows were pointing up. In our second example, the end behavior, our arrows are pointing down. All right, now let's look at this one. In this example right here, let's look at this one. So again, this is a polynomial function. My domain's all real numbers. And it's smooth and continuous. There are no gaps, no sharp turns or anything like that. So your turns are smooth. Those are smooth turns. So let's look at the end behavior of this function f of x. So again, remember what we mean by end behavior. What's happening to the far left and what's happening to the far right. Now this time, notice that the arrows are in different directions. So this is going up, this is going down. All right? But it's still intuitive, just like we've been doing with these. It's still that same idea. So as x approaches positive infinity, what is f of x approaching? And as x approaches negative infinity, what is f of x approaching? That's the question. Okay? So as x approaches infinity, remember what that means. That means as x gets bigger and bigger and bigger, look at that end behavior. What are my y values doing here? Well, remember, the arrow is pointing down, so your y values are approaching negative infinity. Over here, as x approaches negative infinity, so as x gets smaller and smaller and smaller, what are those y values doing? Well, those y values are getting more positive, right? They're getting more positive, so hence your y values are approaching positive infinity. So that pattern's that same thing. So remember, when your arrows point up, your y values are approaching positive infinity. When your arrows point down, your y values are approaching negative infinity. Same thing here. Notice your your arrow is pointing down. So hence, as x gets bigger and bigger and bigger, your y values get more negative. And your arrow is pointing up. So as x gets more smaller, I keep saying it's more smaller, but I mean smaller and smaller and smaller, your y values are becoming bigger. So positive infinity. All right, so let's look at this example. So in this example, again, we don't care about what happens. When we talk about end behavior, it does not matter what happens between these arrows. We're just interested when we talk about end behavior. When we say end behavior, we're interested at what happens on the outsides, on the far left, the far right. I don't care about what happens anywhere in here. Okay, so when we mean end behavior, we mean this. So notice that again, that same notation. So as x approaches infinity, what is f of x approaching? What are my y values? What's happening to my y values? So as x gets bigger and bigger and bigger, look at that end behavior. Y values, see this arrow is pointing up, so your y values are getting bigger, aren't they? All right, so your y values are approaching infinity. So as x approaches negative infinity, so on the other side, on the far left, so as x gets smaller and smaller and smaller, what are those y values doing? Well, those y values are becoming more negative. So f of x is approaching negative infinity. All right. Now, those are the only four. When we talk about polynomial functions, you're going to see that the graphs of all these polynomial functions, this is what happens to the end behavior. Either the arrows are pointing up, or the arrows are pointing down, or the arrows are in opposite directions. On the left side is pointing up, on the right side is pointing down. Or on the left side it's pointing down, on the right side it's pointing up. So for every polynomial function, you have one of four situations. Okay, so for every polynomial function, so all polynomial functions, you will have the end behavior. You will have the end behavior being one of these. Four situations. And I can't spell this. Okay, situations. All right, so either the end behavior, and we're talking about the end behavior, so either your arrows are pointing up, okay, comma, or your arrows are pointing down, just like this. Doesn't matter what happens between them, right? I don't care what happens between them. I'm only interested in, when we talk about end behavior, I'm only interested in what happens on the far left and the far right. Or your arrow could be pointing down on one side, and on the other side, it could be pointing up. Or your arrow could be pointing up on one side, and then the other side pointing down. So those are the only four situations you will have. Okay? Now, what we want to do next is this. So given a polynomial function, see here in our examples, I gave you the graph, correct? What's going to happen though is that the graph won't be given. The graph will not be given. What's going to happen is you will be given a function. You'll be given a function just like we talked about at the beginning. If I can find it real quick. You will be given this, and you will be asked to describe the end behavior. And it is very easy to do. So given this, you will have to describe the end behavior. So either in standard form or in factored form, you'll have to describe the end behavior. Okay? But at least we know this now. At least we know the terminology. So that was important. So the terminology, as x approaches infinity, f of x approaches either negative infinity or positive infinity. So if your arrow is pointing up, that means f of x is approaching positive infinity. If your arrow is pointing down, f of x is approaching negative infinity. Okay? All right, now let's review one more thing. Okay, so I want to review the, remind ourselves how to find the degree of a polynomial function. Now remember, the degree of a polynomial function is the largest exponent. And we kind of talked about that at the beginning of this lesson as well, but we really talked about this in part 1. Now remember, a polynomial function can be given to you in one of two ways. Either standard form, where it's listed term by term, see the terms, or in factored form. If it's standard form, it's easy. It's easy to determine the degree of the polynomial function. If it's in factored form, it's a little bit more difficult, but it's easy as well. All right, I shouldn't say it's difficult. It's not as easy as this. All right, but it's doable. And you're going to see how to do this. Okay, so let's look at this example. So we're going to start with a simple example. So let's look at this one. F of x is equal to negative 5x to the 4th plus 3x squared minus 7x. So let's say we had this polynomial function. So remember, the degree of f of x is, and remember the degree is the largest exponent of the variable. So this variable, the exponent is 4. This variable, the exponent is 2. This variable, the exponent is 1. So the degree is 4. Okay? Now before we go on, remind ourselves what the leading term is. So the degree is 4. Recall the leading term. Now remember, the leading term doesn't mean the first term you see. The leading term is the term that has the largest exponent. So that's this. So the leading term is negative 5x to the 4th. That's your leading term. Okay, so that's going to be important in our discussion in a little while. So that's that. So keep that in mind. Number 2, let's suppose our function is this. So we have 8x to the 3rd power minus 7x to the 4th plus 6x squared plus 5. Let's say we had that. Okay, so we had this polynomial function. It's listed term by term. Now, keep in mind it's not in descending order, but we can still determine the degree. Now, be careful. Remember, the degree is the number, or is the largest exponent of the variable. All right. So this is 3. This is 4. This is 2, and your constant term has the degree 0. So the largest one listed is 4. So the degree is 4. Okay, now before we go on, let's remind ourselves what the leading term is. So the leading term, remember, the leading term is not necessarily the first term you see. The leading term is a term that has the largest exponent. So that's this. Now be careful. You must include the sign. So don't say the leading term is 7x to the 4th. The leading term is negative 7x to the 4th. So that's important. So the leading term is negative 7x to the 4th. Okay? All right, now let's look at this one. Let's do one that's in factored form. So let's suppose we had h of x equal 6x minus 2 times 3x plus 1. Let's say we had that. Okay? And so I want to find the degree of this polynomial. All right, but it's in factored form. If it was in standard form, it'd be easy to determine, but this is in factored form. I want to remind you about this. If I were to FOIL this out, so you have two binomials. If I were to FOIL this out, if you FOIL, you would get 18x squared, and then the outer and the inner. So the outer is 6x, the inner is negative 6x, so that's 0, and then minus 2, right? So that's what you would get. So h of x, that's h of x. Okay? So if you look at this, the leading term of h of x is 18x squared. And so the degree of h of x is 2. All right, degree of h of x is 2. So here's the point I'm making, though. If you are going to find the leading term of a polynomial, and you will need to in what we want to get to in this lesson, what you need to do is look at each factor and then take each leading term of each factor. So if you look at this factor here, the leading term is 6x. If you look at this factor here, the leading term is 6x, because if you look at this factor, if you cover this one up, 6x to the first, so that's your largest exponent right here. And the same thing here. And so you do is you take the leading term of each factor. So you take the leading term of each factor, you multiply. So as you can see, you're multiplying. So 6x times 3x, so the leading term is 6x times 3x, which equals 18x squared. And then once you find the leading term, you know the degree. So the degree is 2. Okay, now both of those are going to be important in what we're going to be doing in a little while. So let's kind of look at another one. So let's suppose we had this. K of x equals 2x minus 3 times 3x plus 5 times 5x minus 1. All right, let's suppose we had that. So notice that k of x, this polynomial, I have 3 factors. So if you're going to find the leading term, so remember the leading term is going to be the product of each leading term of each factor. So if you look at this first factor, what's your leading term? Your leading term is 2x. If you look at this factor, what's your leading term? Well, your leading term is 3x times. And if you look at this factor, your leading term is 5x. And so if you multiply this out, and use your calculator if you need to, but if you multiply this out, 2 times 3 times 5, that's going to be 30. And then x times x times x is 30x cubed, 30x cubed. So that's your leading term. So that's how you find your leading term. I don't care about anything else. The leading term, to get the leading term, all you do is take the leading term. So you get the leading term of the polynomial, you take the leading term of each factor, and then you multiply them out, and there's your leading term of k of x. So the leading term of k of x is 30x cubed. So the degree of k of x is 3. All right? Okay, now let's look at this one. So let's have one more, and I think you'd be fine with finding the degree and the leading term of a polynomial in factored form. Okay, so let's do number 5. Number 5, let's suppose we had this. Let's suppose we had f of x is 3x times 2x minus 1 times 3x plus 4. Let's say we had that. Okay? And so the leading term, if I want to find the leading term of f of x is going to equal. All right, so I take each factor. All right, now be careful. See this factor, there are actually 4 factors here. There's a 3, an x, a 2x minus 1, and a 3x plus 4. Okay? Now, these factors are monomial factors. These are binomial factors. So the leading term, your leading term, must include the monomial factors as you see them. So that means I see a 3, I must use a 3. I see an x, I must use an x. And then let's go to the other factors. In this binomial factor, what is the leading term? Well, the leading term is 2x. In this binomial factor, what is the leading term? Well, the leading term is 3x. And then you just multiply. So 3x times 2x times 6 times 3x, that's going to give you 18x cubed. All right, so if I were to multiply this out, if I were to multiply all these factors out, my leading term would be this. Okay? And so the degree of f of x is 3. All right, number 6. Number 6, suppose we had g of x is equal to negative 2x cubed times 3x minus 1 times 2x plus 5. Let's say we had that. Okay? So again, you need to look at all your factors. So I have a negative 2, I have an x cubed, I have a 3x minus 1, and I have a 2x plus 5. Okay? And so my leading term, we got to include all your monomial factors. So I must use negative 2, I must use x cubed, and then let's look at this. So your binomial factor, the leading term is 3x. Over here, your binomial factor, the leading term is 2x. So if I multiply this out, I get a negative 2 times 3 times 2. So that's a negative 12. I get x cubed times x is x to the 5th. Okay? All right, so that's negative 3, x to the 5th. That's your leading term. So the leading term of g of x is this. Your degree, the degree is 5. Okay? So the degree is 5. All right, so that should be enough in terms of examples of finding the degree. Now, when we get into multiplicity later on, we're going to use other exponents than 1. See how this binomial, my exponent was 1, 3x minus 1 to the first power, 2x plus 5 to the first power. When we talk about multiplicity later on, we're going to come back and we're going to discuss again the idea of leading term. Okay? All right, now. Okay, so now we want to look at the leading coefficient test. So we know what the leading term is. We know what the coefficient of the leading term is. It turns out that the leading coefficient test, which involves the leading term, that will determine the end behavior. So if you recall when we looked at these end behaviors, so those end behaviors are actually determined. They're actually determined by the leading term. All right. So the leading term will determine whether the end behavior points up on both sides, points down on both sides, points down on the left, points up on the right, points up on the left, points down on the right. All right. So all that's determined by the leading term, and so we use what's called the leading coefficient test to help us. Okay, so in our problems that we just did, I want you to recall that when we looked at the degree, so the degree of any polynomial, either the degree is even, see that degree is even, or the degree is odd. Okay, so either the degree will be even or the degree will be odd. All right, so that's something we need to use in our discussion. All right, so the degree of a polynomial is either even or odd. Okay, even or odd. And notice I left some space here because I may need some space as we go through the discussion. So either it's even or it's odd. Okay, what I want to do now is this. I want to look at some examples of graphs of polynomial functions where the degree is even. Okay, so let's look at even first. All right, so look at this. So notice you have this polynomial function. What is the degree of this polynomial function? Well, note the degree. Let's talk about the leading term. So the leading term is what? Leading term is 2x squared. The degree is 2. Okay? All right, so the degree is 2. Notice the end behavior. Now let's talk about the end behavior. Notice the end behavior. What happens with the end behavior? The arrows are pointing up, aren't they? So notice the degree is even. The degree is even. Y'all agree? All right, degree is even. Notice the end behavior. The end behavior is pointing up. All right, now we'll look at this one. Over here, here's the function f of x. Looks like this. Okay. The leading term is 3x to the 4th. Leading term is 3x to the 4th. The degree is even. What do you notice about the arrows? They're pointing up. They're pointing up. Okay? All right, now, listen carefully to this now. Let's look at this one. The degree is even, right? So the leading term is negative 2x squared. Remember, you got to keep that sign. The degree is 2. So the degree is even. But here's the question. You see over here, over here, the arrow's pointed up. The degree is even. The arrow's pointed up, right? Over here, the arrow's pointing down. So in my end behavior, the arrows are pointing down. What, if you recall when we graphed quadratic functions, now these are quadratic functions, why do you think the arrows are pointing down here and the arrows are pointing up here? Why is the parabola here opening up and why is the parabola here opening down? So if you recall from a previous lesson that we talked about when we graphed quadratic functions, the coefficient of the leading term, which is negative, indicates that it's a reflection. So your arrows are pointing down. Okay? So notice this coefficient. So the leading coefficient is positive, right? The leading coefficient is positive, so the arrows point up. Okay? The arrows point up. So if the degree is even, and the leading coefficient is positive, in this case the leading coefficient is 2, positive, the arrows point up. Okay, let's look at this. Over here, the leading term is negative 2x squared. The leading coefficient is negative 2. Okay, the degree is even. So if the degree is even, either it points up or they point down. Okay, they point down if the leading coefficient is negative. So the degree is even, the leading coefficient is negative. It's really negative 2. So the arrows point down. Okay? The arrows point down. Okay, if I go back to this one where the degree is even, notice the arrows point up. Why do the arrows point up? Well, look at the coefficient of the leading term. The coefficient of the leading term is positive. So the coefficient of the leading term is positive. In this case, it's 3. So the arrows point up. Okay? So the arrows point up. All right, let's look at this one real quick. So notice the degree of this polynomial. Here's the graph. The degree of this polynomial is 4, so it's even. Okay, so note the leading term is negative x to the 4th, right? Okay. The degree is 4, which is even. Okay. And what makes it go down? What makes the arrows, what makes those end behaviors point down? Well, it's the leading coefficient. The leading coefficient is negative. So in this case, it's -1. So since the leading coefficient is negative, in this case -1, the arrows point down. Okay? All right, now let's go back to, let me find it real quick. Let's go back to this. Okay, so if it's even, it's kind of easy to know what to do. Okay, so listen carefully. If the degree is even, now remember when we look at the leading term, we use this notation for the leading term. We use this notation, a sub n, x to the n. That was the notation for the leading term. Okay, so I'm going to use a sub n in my discussion. So if the degree is even, so if n is even, we're talking about n here, the exponent. So if the degree is even and a sub n is positive, a sub n is positive, meaning the leading term is positive, your arrows point up. So do something like this, okay? If a sub n is negative, so if the leading term, the leading coefficient is negative, your arrows point down. All right, so even degree is easy. Even degree is easy. And what I would do to help me with remembering this, now don't memorize what I'm putting here, don't memorize. That's not the intent. The intent is for you to understand what happens to the behavior in the ends for an even degree, what happens to the behavior at the ends for a polynomial with odd degree. And the way I would do that is this. Okay, I would just remind myself about x squared and negative x squared. So remember x squared, the parabola x squared, the degree is even, right? So just remember x squared. Well, what does x squared do? Well, that's a polynomial function. So the degree is even, so it opens up. Negative x squared, remember what that looks like. So again, I didn't draw this very well right here, but it opens down, so the arrows are pointing down. Okay, so the degree is even, the degree of e is even, and the coefficient is positive, the arrows are pointing up. If the degree is even and the leading coefficient is negative, the arrows point down. Okay, now one other thing I got to remind you about this, the notation. So remember this right here, so this right here means this. As x approaches infinity, so as x gets bigger and bigger and bigger, your y values, f of x, approaches infinity. As x approaches negative infinity, so as x gets smaller and smaller and smaller, your y values approaches positive infinity. All right? Now again, don't memorize this. Just remind yourself, just looking at this, at the end behavior, as x gets bigger and bigger and bigger, your y values are getting bigger. They're becoming more positive as you go this side. For this one, as x approaches infinity, what's happened to your y values? Well, they're getting more negative, right? So f of x approaches negative infinity. So notice the arrows are pointing down in both situations. So as x approaches negative infinity, f of x approaches negative infinity as well. Okay? All right, now let's talk about the odd. All right, so remember our situations, our four situations. So our four situations was this. So we had our arrows pointing up, our arrows pointing down in both directions, on both ends, and then we had on one end the arrow pointing up, on the other end the arrow pointing down, on the other pointing up, on the left side pointing up, on the right side pointing down. So this right here, this two situations occurs when the degree is even. So the degree is even, is this right here, okay? Over here, that would occur if the degree is odd. So the degree is odd. That would be these two. Okay, so the degree is odd. And that's easy to remember because look, here's what I would do for an odd degree. I would remind myself about x cubed. So remember, x cubed looks like this. All right, so remember when you plotted the points, and so that was the graph of x cubed. So notice on one side, on the left side, it's pointing down. On the right side, it's pointing up. Okay? And then when I did negative x cubed, somebody used an orange for that. When I did negative x cubed, or red, whatever color this is, so I would get this graph. Negative x cubed. So I would get this. All right, and so this one here would be f of x. Let me not use a different function. G of x equal negative x cubed. All right. So if the degree is odd, you get one of these situations. So on one side is pointing up, on the other side is pointing down. On one side is pointing down, on the other side is pointing up. And here's the way I would remember this. Think about x cubed. Well, if you graph x cubed, on the right side is pointing up, on the left side is pointing down. Negative x cubed is just the other way. On the left side is pointing up, on the right side is pointing down. All right, so let's look at some quick examples, and then we'll come back and we'll look at this. Okay, so we have this function g of x. Notice the leading term is 2x cubed. The degree is 3. All right, so the leading term is 2x cubed. The degree is 3, so that's odd. Degree is odd, right? And I want you to notice the in behavior. So on one side, the arrow is pointing up. On the other side, the arrow is pointing down. I don't care what happens in here. That's another discussion. I'm just interested in the end behavior. So I know that on one side it's pointing down, on the other side it's pointing up. I also know this. I also know that x cubed, this blue graph right here, on the left side it's down, on the right side it's up. Okay? The coefficient is positive 1. That's a positive 1, so the coefficient is positive. So I know this. I know that since the leading coefficient is positive, in this case it's 2. Okay? So what that means is this. So the end behavior will be this. On the left side, it points down. On the right side, it points up. Okay? Left side, right side. So this is the left side. This is the right side. Okay? All right, let's look at another example. So over here, let's do this one. So again, here's another example where the leading term is odd. So, or I'm sorry, the degree is odd. So the leading term is 3x cubed. Okay, the degree is 3, which is odd. All right, so I know that since it's odd, the arrows are pointing in different directions. The arrows are pointing in different directions if it's odd. If it's even, the arrows are pointing in the same direction. Okay, now the coefficient of the leading term is positive, which in this case is 3. So that means the end behavior will look like this. So it's going to point down on the left, point up on the right. Okay? Point down on the left, point up on the right. And that's what you see. So you see that the left side is pointing down, the right side is pointing up. And then let's look at this one. Let me get it real quick. All right. So this one. So notice this time the end behavior, is pointing up on the left and pointing down on the right. Okay, so whenever the arrows are pointing in different directions, the degree is odd. So we know the degree is odd, and it is, because what's the degree? The degree is 3. So the degree is 3. So that's odd, which is odd. All right. And the leading coefficient is -2, which is negative, right? So since it's negative on the end behavior will look like this. So on the left, it points up. On the right, it points down. Okay, so on the left, it points up. On the right, it points down. Okay? All right, so what I want to do now is kind of summarize real quick what we just learned. Okay, so I know that if the degree is even, the arrows are pointing up or they're pointing down. They're pointing up if the leading coefficient is positive. They're pointing down if the leading coefficient is negative. If it's odd, we get the situation where on the left side it points up, on the right side it points down, or we get a situation where on the left side it points down, on the right side it points up. But if it's odd, notice that the arrows are in different directions. The end behavior, the arrows are in different directions. So remember when we did when we looked at the leading term, so the degree is odd, the arrows are in different directions, right? If the coefficient is positive, so if a sub n is positive, we get this. So on the left side it points down, on the right side it points up. And the way I would do that is I would think of x cubed. All right, think of x cubed. X cubed looks like this. So on the left side it points down, on the right side it points up. So left side points down, right side points up. And what that means is this now. That means as x approaches infinity, so x gets bigger and bigger and bigger, what are those y values doing? Those y values are approaching positive infinity. So f of x approaches infinity. As x approaches negative infinity, so if I go this way, all right, it's kind of easy to see. So as x gets more negative, what's happened to those y values? Well, those y values are getting more negative as well. They're pointing down. So f of x approaches negative infinity. All right, so if the leading coefficient is negative, though, if a sub n is negative, the leading coefficient is negative, then remember it's in different directions. So on the left side, instead of pointing down, it's pointing up, and on the right side, it's pointing down. Okay? And so what that means is this: as x approaches infinity, so x gets bigger and bigger and bigger, what are those y values doing? And let's look at this situation here. If you need to, look at this graph where we had odd exponent, odd degree, negative coefficient. So notice on the left side, as x gets bigger and bigger and bigger, what are those y values doing? Those y values are getting more negative. So f of x approaches negative infinity. And as x approaches negative infinity, so as x gets more negative, what are those y values doing? Those y values are approaching positive infinity. So f of x is approaching positive infinity. Okay? All right, so this is the way I would remember that. I would remember this in terms of x squared. That's the way I would do it. Think about x squared. If I can get those graphs again real quick. Think about x squared. What that does, what the graph of that does, because the degree is even, the coefficient is positive, the arrows in the same direction. Negative x squared, degree is even, coefficient is negative, the arrows are in opposite directions. They're pointing down. I'm sorry, I didn't mean opposite directions. They're pointing down, same direction, pointing down. Okay, so even degree is easy. Odd degree is a little bit harder for students. Again, I would think if it's odd degree, here's the way I would approach this. I would remember myself x cubed. What does x cubed look like? Well, this is what x cubed looks like. So if the coefficient is positive, and it is, because remember, positive 1, on the left side it points down, on the right side it points up. If it's negative x cubed, odd degree, negative coefficient, on the left side it points up, on the right side it points down. That's how I will remember it. Don't memorize this. Don't memorize this. Use these basic graphs that you learned in the past to help you understand how to determine the end behavior. Okay? All right, so I think that's enough for this part 2. So that's going to end this lesson. So I think we're good at this point. Let's see real quick. So in Canvas, when we go to your Canvas pages, one of the files for this is going to be in typed form. It looks like this. So this right here is basically this. All right. So again, don't memorize this. It's not a good idea to memorize this. Do not do that. You need to understand what all this means in terms of even degree, odd degree, and whether the leading coefficient is positive or the leading coefficient is negative. Okay? All right, so that'll be the end of our lesson on end behavior.